This is the title page from my PhD thesis. My PhD advisor, Dimitri Saltis, proposed to build artificial neural networks using optical devices. This figure from the thesis shows the concept of a biological neural network consisting of neurons and connections between the neurons. The next figure then shows a holographic optical implementation of this kind of connectionist machine. At the time of this work, neither optical information processing nor neural networks were practical. 35 years later, neural processing is an increasingly dominant computational model. Optical devices, especially through the development of fiber communications, have also advanced enormously, but optical neural networks remain dreamware. Through this series of videos, I hope you will find that there are enormous opportunities in computational imaging. But if you pursue these opportunities, you will find that there are also enormous challenges in bringing technological dreams to reality. Technology moves very fast, but also very slow. Amazingly, over 75 years after the idea was proposed, processing hardware specifically designed for neural processing is only beginning to come to market. One sometimes hears fears that AIs will replace humans, but the real question is whether or not humans can rationally develop the opportunities before us. Today, NVIDIA's market capitalization has gone beyond $1 trillion because its GPUs are the default platform for neural processing. The application of GPUs to connectionist machines is accidental, however. They are not designed for this purpose. The real power of neural processing will be in new hardware architectures designed for the tasks. Intel's HaloPoint project is an example of efforts in this direction, shown here with an owl in the background because it supposedly has roughly the processing capacity of an owl brain. HaloPoint has 1 billion neurons and 128 billion synapses. It is not really analogous to a biological system. Electronic neural networks are different beasts, but what systems like this can do as computing hardware remains to be seen. One thing extremely clear at this point, however, is that neural processing is a revolutionary technology for estimating objects from measurements. Let's talk about how to use it in computational imaging.
Computational imaging.
Episode 17, Artificial Neural Networks. So we return to the central challenge of computational imaging, estimation of the object from measured data. So we have a variety of different measurements of the object, and we want to turn that into an estimate of the object, which we'll call the image. We've assumed that the image is an object distribution, but one may also, or alternatively, seek to identify the object or to abstract object parameters. The challenge begins with the data and ends with the estimated image. In between lies a processor, represented here by a literal black box. Up till now, we assumed that the black box implements linear regression on the forward model, but recently much more sophisticated algorithms have emerged. Episode 16 focused on Bayesian estimators, but Richardson-Lucy estimation is still locally based on the forward model. More advanced machine learning algorithms enable Bayesian estimation using disjoint and feature-specific estimators. Here we show the possibility of multiple different sampling manifolds may be combined, for example, different color planes, different perspectives, or different spatial temporal filters in image estimation. We turn that into a picture of me in my younger days out sailing. If only we could go back then, but let's focus instead on the workhorse of the neural estimator, which is going to be the perceptron. We encountered perceptrons in episode 8 in discussions of neural representation. The basic perceptron is a linear projection of an input vector represented here as I with the weight vector W. This inner product is thresholded by an activation function to produce an output. The net effect is to segment a hyperplane defined by the weight vector. This is illustrated here by hyperplanes separating cats and dogs with the two-element weight vector representing animal size and tameness. The goal of the perceptron may be to identify cats and dogs. By choosing various weights, one achieves various degrees of success in this goal. So these different lines that we see correspond to different weight vectors. And we try to separate the cats and dogs, but we may or may not be successful with the simple perceptron. If we can't do it with the simple perceptron, we can improve our estimation by adding more perceptrons to our model. Here we show a multi-layer perceptron with a single hidden layer. We have each perceptron has its own weight vector and its own inputs, and then we get the outputs y. So these are our weight functions and our activation functions. And then by determining the weights and the biases going into the system, we have a set of learnable parameters that we can use to implement a transformation between the inputs and the outputs. So we saw back in episode 8 that the complexity of the mapping depended on the activation functions and the hidden layers. So with different activation functions and different network complexity, we can implement much more complex segmentation than simple hyperplane segmentation. In practice, we're interested in much higher dimension input planes and deeper networks. So how do we apply neural processing to image estimation? This is a deep and evolving question. This course focuses mostly on computational imaging system design, by which we ultimately mean which physical measurements to take. Given the measurement data, there is no end to the strategies one may employ to estimate the object and its parameters. Ultimately, we will need to consider algorithm-independent measures of computational imaging system capacity, such as forward model conditioning and feature structure. But we also need a basic understanding of how one may implement image estimation. The key to this is to understand that the measurement data also typically consists of images. There are specific ways to handle images in neural architectures. Consideration of this question brings us back to this slide from the very first episode in this video series. Images are ordered lists. So we think of an image as an array of numbers, as shown here, and the numbers are indexed by indices I and j, and so there's an adjacency between pixels in the image. And so we can create images by these pixel values. Alternatively, we could also think of images as features over the pixel ranges. So in previous episodes, we talked about singular value decomposition of the forward model. The singular values, or the singular vectors corresponding to the singular values, correspond to features that are measured by the forward model. But the images themselves can be built from features. Here is an example. We show a figure from chapter 8 of the text where we decompose a hyperspectral image into its features. So here, this horizontal axis is wavelength in nanometers, and the vertical axis is pixel position in the image. And this array is a set of features that we can use to most efficiently construct the image. So rather than decomposing the image into a pixel basis, we can decompose it into its underlying features. An ideal imaging system might seek to directly measure these blocks and define them to represent the image. How would we find these kind of features in an image? Well, one way to find features in an image is to use a matched filter. So given a pattern here, phi of x, we can convolve with the conjugate of phi of x and to implement a matched filter. So this matched filter, m of y, would be our output value from the matched filter. We do this by convolving with phi of x, which means we integrate the product of phi of x with a shifted version of phi of x. And here, as we shift across, you find that the maximum value of the integral will occur when the patterns are aligned. So the autoconvolution is peaked at 0. We can use this peak to find this feature in an image. As an example, here we have a smiley face and a frowny face. If you look in the code that comes with the course, you find that we can generate a pattern of smiley faces or frowny faces by choosing some random positions, x and y, and then placing the sad face, let's say, at every point in the randomly selected positions. And then we find where those sad faces are by convolving with the matched filter, which is done in this line. And then we'll threshold on the matched filter to find those positions and create a binary map of positions of the sad face. And then we're going to convolve with those peaks of the matched filter to replace the sad face with the smiley face. And that's done here. So we have an image of a bunch of randomly placed smiley faces. Here's the matched filter values. And you see that the peak is at the center, but there's some value around that. We threshold, we get little tiny dots that you can hardly see here. But we convolve with those delta functions, and we've turned the smiles upside down into, or the frowns upside down into smiley faces. So this can be thought of as a neural operation. So here's our input image with the frowny face. And then the convolution is, each point is taking a matched filter, which we would represent as weights operating on the object. And we take those and put into a thresholding, a network, and get a thresholded value. If we want to shift that weighted value around, the convolution is implemented by just taking the same weights and operating on the next set of pixels and getting a value. So this is what this operation is, the basis for what's called convolutional neural networks. So a convolutional network takes an input image, convolves it with a bank of filters, goes through thresholding and other operations in a succession of operations to produce a transformed image with new filter functions. Now, if the network was going to be used to classify objects, it may also have some fully connected network structures after a series of convolutional layers, but we can implement a wide variety of systems using convolutional layers alone. Each convolutional layer is implemented by a bank of filters. So the operations on images with different kinds of filters produce different feature maps. So a convolutional network transforms an image, a data structure where each pixel has a representation similar to other pixels, into a new feature map. Basically a bunch of pixels, but now the pixels consist of feature values. And we implementing this basic operation with a lot of different filters and different thresholding functions, we can implement very interesting operations on images and transform one image distribution into another. As a simple example, let's look at a classification network. So this is an example where we're going to classify hand-drawn digits from the modified NIST data set. And the network takes a input layer. The images it happens are 28 by 28 pixel maps of the hand-drawn features, and then goes through a series of convolutional layers. Now here, this number is the number of filter functions we're implementing. So we're taking an image and convolving it with 32 different filters, and so we get an output value at every pixel for every one of those filters. There's also some layers here that do some max pooling, so they choose the maximum of the filter functions to help us classify and segment the image. And then at the end, the image is flattened into a feature map that we'll use to classify the figures. So obviously there are a bunch of choices in the network structure shown on the previous slide. How did we decide, how many layers, how many filters to use, and what the network structure should be? Well, in this case, I did that the easy way. I went into Google Colab and I prompted it with create a neural network for classifying digits on the NIST dataset, and it created the network shown here that was illustrated on the previous slide. The prompt also gives us the code we need to train the network. So xtrain is examples of handwritten digits, and ytrain is the identification of those digits. So this is a supervised training model with a known output. Xtest and ytest are examples we can use to test the network after we've trained it. The number of epochs is the number of times the training cycle will go through all of the examples we have on the network. So already after the first epoch for this simple network, we have 95% accuracy in identifying the handwritten digits, and after 5 epochs, we have 99% accuracy. So let's test the network now. We can go and draw a handwritten digit or two. Here's some examples, and let's see how the network does on these examples. So now through the magic of video, I saved the hand-drawn pen drawings I put on the previous slide, and then read them into NumPy, and then rescaled them to produce the images that are shown up here. And then we can take them into the model that we just trained and predict what the model thinks that they are. And in the case of the 8, it correctly believes that that's an 8, as shown down here for the predicted class. And if we take the hand-drawn 7, we find that the model correctly predicts that to be a 7. But for whatever reason, the hand-drawn 9, we're going to test our 9. We find that it also believes that to be a 7. So obviously the model's not perfect, and we could continue to work and understand why that is. But let's instead use this as a way to think about what the network is doing. So this network has 32 filters in the first layer, and we can visualize what the network is looking at, the kind of features it's looking at, by looking at how they operate on a individual input. So here we've input a 7, and we see that the filters are taking various forms of derivatives to highlight the edges of the 7. We can also analyze what the network is doing by looking at the filters themselves. Now in this case, the filters are not complicated images. They're 3 by 3 little filter sets, and so we're measuring 32 different 3 by 3 filter projections. And if we go to successive layers, we can find, for example, in the 4th layer of the network that we have 64 filters which are output a 5 by 5 image after we've done some pooling. So the idea is to take the input structure that we have in the form of an image and turn it into something that's representative of something that a machine could understand. Now in this particular case, since we want to classify the image, we take the image after we've gone through and got all these filters and turn it into a flat image with 1600 components, and then that goes into a single layer perceptron that classifies it into 1 of 10 classes, the integers 0 through 9. And so we can look, for example, here's an example of some randomly drawn 7s from the data set, numbers that happen to be identified as 7. You see what the 1600 element features look like. And in contrast, you could see on the right what the a bunch of numbers, 9 different numbers that happen to be 8s, what kind of features they produce. So you could wonder, could you look at these and identify whether that's a 7 or an 8? But now the data has been turned into something that's no longer an image. There's no preferred order for these 1600 values, and so there's no reason that you should be able to look at that and identify it by eye, but this is now in a form that a machine can identify it. And so the point of this discussion today is just to introduce this concept of convolutional neural networks and the convolution as a basic feature for processing images. The other thing that's important from today's discussion is to understand how this kind of classifier was built. It needed somehow to figure out what the weights are that will do this classification. And for that, it uses training. The training is based on error backpropagation. So in this particular case, we have 60,000 or so hand-drawn digits with their identified value of what they are, where a human has looked at them and identified what they are. So we sample a batch of those digits, feed it through the network, and then find the error, find where the network has failed, and then we take a gradient descent process to backpropagate those errors and correct the weights. And it happens now if we go through, literally hundreds of thousands of operations to backpropagate those errors, we can use this network structure to build a classifier that will correctly identify the digits. So our goal is not to understand in all details how backpropagation is implemented, what those algorithms are. Our goal is to use this to transform images from the form of measured distributions into estimations of the scene. And so what we're going to do in the next slide is apply this to a particular example. Here we have a color image that was taken with a system that has a RGB filters on it. So if we look into details of a raw version of the image shown here, you can see that it consists of these blocks, and it turns out that these dark blocks correspond to blue here, and then we have red, green, and blue filters. And so somehow a measurement system needs to transform this RGB data into the color image that we see behind it, and that process is called demosaicing, and in our next discussion we're going to build a neural network to implement this process.